Hello, this is the Ocean Engineering System Design and Control Final Design Review presentation for the Wave-Powered Autonomous Surface Vehicle.
My name is Emmanuel Roig, and I'm the team leader of the group, along with the position of a software engineer. To the right of me is Carlton Jones, another software engineer, and the person in charge of progress tracking. Following is Derek Hooker, an electrical engineer, and the electronic shop coordinator. In the bottom left is Luis Julian Velasquez, another electrical engineer and the person in charge of environmental hazards and safety. Following to the right is Logan Riley, a mechanical engineer and the person in charge of purchasing and budgeting. The last student in our group is Tanner Reynolds. He is part of the mechanical engineering team and the person in charge of coordinating the machine shop. Here I will discuss the project overview, where the goal of the wave-powered autonomous surface vehicle is to have a system that can collect and store energy from ocean waves in a given range of wave height conditions, and use this energy to conduct a mission which permits researchers to have the device that has increased operational time without the need of retrieving the vessel for a constant recharge. Our objective and requirements are: the vehicle shall be 2-man deployable. The vehicle shall harness wave energy in 0.3 to 1 meter waves. The vehicle shall travel 200 meters to a waypoint in 600 seconds or less, and 200 meters back to its initial position, all within a 5-meter accuracy. The vehicle shall correct its position accordingly while navigating. The vehicle shall harness energy and measure and record the energy being stored. The vehicle shall store enough energy to complete the whole mission. The vehicle shall be tunable for trim and increase energy harvesting efficiency. The vehicle shall have the capability to repeat missions to increase the reliability of the system. Some existing technologies that are relevant to this project are the point observer, which uses the vertical motion of the buoy to activate a power system. The attenuator. These devices capture energy from the relative motion of the two arms as the waves passes them. The oscillating water column. As air is driven in and out of the chamber, this will drive a turbine which will generate power. The approach taken to complete this project was divided into mechanical, electrical, and software. For the mechanical aspect of this project, a simulation was done to predict the RPM of the spinning mast. Other analyses were done, such as stability and stress analysis on the system. In the electrical department, a motherboard was created to connect the GPS, compass, linear actuator, current sensor, and temperature sensor. The software team of this project was in charge of making a navigation code for the ASV with the use of a proportional controller to correct the ASV heading. The software team used Arduino software to write code for all electrical components. Mechanical design outcomes. When the ASV is deployed, the rotating mass will spin around clockwise or counterclockwise, which will activate the port or starboard generator. The rotating mass is connected to a vertical shaft and supported by the aluminum superstructure. The vertical shaft connects to the gearbox, which transfers the energy to the motors. The motor mounts are extended so that the thrusters do not come out of the water when transitioning through waves. The keel has a removable cap to add or remove weight to make sure that the ASV will be stable and calibrated to get the most energy without capsizing. The safety cage was added around the rotating mast to avoid injury when deploying and retrieving the ASV. Also seen here is the electronics box where all the electrical components are stored. On this slide we have a picture with our PCB fully populated. These components were carefully soldered and placed on the board at the electronics shop on campus. Each component plays an important role for making the system work. On the board we also have connectors, which is basically where the electrical wires are connected to and from components. Our PCB board is powered by a 12-volt battery, which is connected to a bus bar which distributes power to the components on and off the board. The software design was broken down to 4 categories. The first one is initialization. Here, the ASV checks to make sure that all electrical components are operating correctly. Next is the energy collection case, where the ASV disengages the boom brake to let the spinning mass spin when the waves approach it. While doing this, the ASV is using a current sensor to calculate the power being harnessed from the generators. Once sufficient power has been produced, the ASV will go into the transient to objective case, where here the brake is applied to the spinning mass, where it is then aligned with the stringer of the ASV. The ASV now navigates 200 meters to its waypoint and makes a 180-degree turn and navigates back to its initial position. After the ASV has completed its mission, the shutdown routine is called. Here, the data is saved into the SD card and the ASV power system is then deactivated. Achievements. Theoretical calculations prove that the ASV will generate sufficient energy to complete the mission in 4 hours and 10 minutes. This is on a day where the waves are 1 meter high and at a period of 3 seconds. Due to COVID-19, the actual model was not tested at sea. The wave-powered ASV team would like to give special thanks to the FAU faculty and staff and the Department of Mechanical and Ocean Engineering for helping us with our project.